Today I am going to discuss about the design strength calculation of laterally supported beam with high shear. In last lecture we have discussed the design procedure for calculating the section size of a beam member due to laterally supported beam member due to low shear, and we have seen how to calculate the design bending strength due to low shear and how to design the things, right. Now, in case of high shear, we have seen that certain reduction will be happen because of the high shear in the bending moment calculation, bending strength calculation. So, bending strength due to low shear whatever will come, it will be less in case of high shear. So, some reduction will be there, that we will see, and the formula whatever we have discussed earlier, based on that we will try to find out the design bending strength due to high shear. And let us go through one example. The example is this: that design a laterally supported beam of effective span 5 meter with the following data. Say grade of steel is used Fe410 and maximum bending moment is suppose 180 kN and maximum shear force, factor shear force is coming 220 kN. And as we are going to calculate only the the bending strength due to laterally supported beam due to high shear. So, we are not going to check for deflection, as this will be same as we have done earlier. So, let us see. So, first what we will do, we will try to find out the ZP required, that is the plastic section modulus required, ZP. So, ZP required will become m by Fy by gamma m0. So, the maximum bending moment, factor bending moment has been given as 180 kilonewton meter. So, 180 kilonewton meter means 180 into 10 to the 6 Newton millimeter into 1.1 gamma m0 and Fy is 250, as we are using Fe410 grade of steel. Therefore, we can find out the ZP required as 792 into 10 to the 3 millimeter cube, right. So, now if we look into the SP6, we can find out an appropriate section as ISLB 350 at say 0.485 kilonewton per meter. If we choose this section, we will see the ZP is coming 851.11 into 10 to the 3, which is more than the required plastic section modulus, right. So, we can in fact we can use higher section also. However, we can try with this and let us see whether it is safe or not. So, if we use ISLB 350, then we can find out its properties like the elastic section modulus, ZEZ also we can find out, which is 751.9 into 10 cube. Similarly, the overall depth H is 350, and the data other data which we will get in SP6 is the flange width. Width of flange was given as 165 millimeter. Similarly, the flange thickness was given as 11.4 millimeter, and thickness of wave is given 7.4 millimeter, and root radius R1 is given as 16 mm. This will be the data which will be required for calculation of the plastic section modulus, actual plastic section modulus, and then the bending strength of the section. So, here the effective depth we can find out. Effective depth will be say d minus, if we say this is H or D, we can say d minus 2 into Tf plus R1. So, 350 minus 2 into 11.4 is the thickness of flange and root radius is 16 mm, right, 16 mm. So, after calculating this, we are getting D as 295.2 mm. So, the effective depth of the wave we are going to find as 295.2 mm. Now, we have to classify the section whether it is plastic, compact or semi compact. So, for that we have to find out the B by Tf. B by Tf means the hanging portion, B means 165 by 2, this will be B, because width of the flange is 165 mm. So, half of that will be B and Tf is 11.4. So, after calculating you can find out 7.23, which is less than 9.4, and D by Tw we can find out. D we calculated as 295.2 and Tw is given as 7.4. So, this is becoming 39.9, which is less than 84. So, from this we can see that the section is plastic. So, from this criteria we can define the section as plastic. So, if the section is plastic, then we have to calculate the design bending strength accordingly. Okay. So, reduction of the strength will be calculated on the basis of the section as plastic. Then we have to see, before calculating the design bending strength, we have to find out whether it is low shear or high shear. So, for that we will check the shear capacity. So, design shear strength of the section we can find out Vd as Fy by root 3 gamma m0 into D into Tw, right. So, Fy is 250 and root 3 into gamma m0 is 1.1 and D is the overall depth 350 and thickness of wave is given 7.4, and if I make into kilonewton, this will become 339.8 kilonewton. So, design shear strength of the section is coming 339.8 and 0.6 Vd, because you have to check, that is becoming 0.6 into 339.8 is equal to 203.9 kilonewton, which is less than the applied shear, means the factored shear which are coming in the beam due to external loading, that is 220 kilonewton, right. So, here what we could see that Vu is greater than 0.6 Vd, right. That means, we can define this as high shear. So, because of high shear, certain amount of bending moment will be reduced with some reduction factor, and then finally, we will get the modified bending moment. And because of this presence of high shear, we will see how to calculate the bending moment. So, first we know the plastic design moment of the whole section disregarding high shear can be calculated as this: M d is equal to Z p z Fy by gamma m0. So, this is means if we do not consider the high shear, then this is the bending moment, means bending strength we will get, which is ZPZ is 851.11 for this section into 10 to the 3 into Fy by gamma m0. So, to make it kilonewton meter, I can multiply 10 to the minus 6. So, I am getting 193.43 kilonewton. So, disregarding the high shear, the plastic design moment of whole section will become this. However, we have to multiply with certain reduction factor to find out the plastic design moment because of presence of high shear. So, for that what we have to find out? We have to find out the section modulus of the cross section excluding shear area. section modulus of the cross section excluding shear area. So, that will become, so section modulus of the whole section is ZPZ and section modulus of the shear area will be AW into YW. So, for that we can find out this is as ZPZ was given 851.11 into 10 to the 3. So, this is ZPZ minus AW. So, if we see the section, say the I section which we have considered, its overall depth is 350, right. So, along the neutral axis this depth will become 350 by 2, right. Now, we have to find out AW. AW is the area of this. So, area of this and plus area of this, right. So, AW will become basically 350 by 2 into 7.4. This is AW into YW. YW means the CG of the area from the neutral axis. So, CG of the area for this, CG of the area will become somewhere here, that is 350 by 4. So, it will be 350 by 4 and for 2 side it will be into 2. So, AW into Y will be the plastic modulus, section modulus of the wave of one side, and for 2 side it will be multiplied by 2. So, ZFD the section modulus of the cross sectional area excluding shear area will become 624.49 into 10 to the 3 millimeter cube. So, ZFD we can find out from this. Now, we can find out the plastic design moment of the area of cross section excluding shear area, MFD. So, excluding shear area, the plastic design moment of the cross section will become MFD as so this is ZFD. So, ZFD 624.49 ZFD into Fy, Fy is 250 by gamma m0, that is 1.1. So, MFD the plastic design moment excluding the shear area we found as 141.93 kilonewton meter, right. So, this is how we can find out the value of MFD. Now, we can find out the value MDV, which will be the modified plastic design moment of the section due to high shear, that is MDV. So, MDV will become basically MD minus beta into MD minus MFD, right. So, and it has to be less than or equal to 1.2 JD into Fy by gamma m0. So, if we calculate this, we can see the MD value we have calculated earlier, that is 193.43, which is the plastic design moment of the section disregarding high shear, and beta value we have to calculate, right, and beta into MD minus MFD. So, beta is the reduction factor which can be written as 2 into V by Vd minus 1 whole square. So, beta value we can find out, 2 into Vu is the 220 kilonewton the shear force, and shear strength of the section we calculated 339.8. So, after putting this value we will get beta as 0.087. So, we will multiply beta means here with beta, that is 0.087 into MD minus MFD. MD is 193.43 minus MFD is 141.93, which we have calculated earlier. So, this is becoming 188.95 kilonewton meter, right, 188.95 kilonewton meter. Now, it has to be less than equal to 1.2 JD Fy by gamma m0. In any case, it has to be less than this. So, this if we calculate, we can see this will become 1.2 into 751.9 into 250 by gamma m0 1.1. So, this is becoming 205.06 kilonewton meter, right. So, what we could see that MDB value is becoming 188.95 kilonewton meter, and it has to be less than this, otherwise this will be considered. So, finally, we can consider the MDB value as 188.95 kilonewton meter, right, and it is greater than the design the factor moment, which is 180 kilonewton meter. So, I can say that the section whatever we have chosen is safe, right. So, this is how one can find out the design bending moment of the section with high shear. So, in fact, what we could see that if it is not high shear, means if it is low shear, we could find out the value as this 193. And because of the presence of high shear, the bending moment is reduced to 180.95 kilonewton. However, this is greater than the factor moment. So, the section is okay. Now, we will go for checking due to buckling, wave buckling. So, we will go for check for wave buckling. Now, wave buckling is not required if d by Tw is less than 67 epsilon as per Poral provision. Now, here d by Tw is becoming 295.2 by 7.4, which is 39.9, and this is becoming less than 67 epsilon. So, in fact, wave buckling check is not required in general. However, because of high shear we need to check this, because of high shear, right. As high shear is present, so we have to check. In case of low shear, we do not need to check this. So, now for high shear, if we have to check, we can check at the support, right. So, at the support maximum shear has been developed. So, if we assume a bearing length of say B is equal to 100 mm, we are assuming bearing length of B is equal to 100 mm. Then the area of the bearing plate we can find out, means the bearing area, that will be A B will become B 1 into T W, right. So, B 1 means B plus N into T W, the area, influence area. So, if we see if the support is here, say for example, this is the section. Now, we have support and bearing length of 100 mm is given. So, it will disperse with a angle of 45 degree, and this will become N 1, right, and this is B. So, B plus N 1, this will become B is given as 100 mm we have assumed, and N 1 will be N 1, as this is 45 degree angle. So, N 1 will be this is the half of the depth, that means 350 by 2 up to neutral axis, right, and into T W the thickness of wave is 7.4. So, if we calculate, we will get this as AB as 2035 millimeter square, right. So, effective the bearing area under influence is 2035 millimeter square. Now, moment of inertia of the effective of the wave we have to find out. Of the wave means this, because of the bearing, that area we have to, means that influence area we have to find out, and accordingly we can find out the I. Before that, let us find out A, the area of the wave. Area of the wave will be simply B into T w. So, B will be 100 into T w is 7.4. So, that is 740 millimeter square. Similarly, we can find out I as B T w cube by 12. So, after putting the value, we can find out the value of I as 3376.87 millimeter to the 4. So, area and moment of inertia we could find. Now, I can find out the effective length of the wave. Effective length of the wave K L will be 0.7 into D. So, that is 0.7 into D we have found earlier, that is 295.2. So, this is becoming 206.64 millimeter. So, effective length of the wave we could find out, and so the radius of gyration we can find out. Radius of gyration will be square root of I by A. So, I is 3376.87 and area is 740. So, this is becoming 2.136 mm. And slenderness ratio lambda also we can find out as effective length by radius of gyration. So, effective length we calculate earlier as 206.64 and radius of gyration we calculated 2.136. So, this is becoming 96.74. So, slenderness ratio of the wave we could find out as 96.74. So, if slenderness ratio is 96.74, then we can find out the compressive stress of the wave FCD, design compressive stress, and that can be found from table 9C of IS 800 2007, because here buckling class is C, and according to this we will follow the table 9C of IS 800 2007, and for that with lambda is equal to 96.74 and Fy is equal to 250, we can find out the FCD value as 111.56 Newton per millimeter. Through interpolation of the data in the given in the table, we can find out the FCD value as 111.56 Newton per millimeter square. So, now capacity of wave section we can find out, say load carrying capacity of the wave FWB, that we can find out that AB into FCD. So, AB we found out as 2035 into FCD as 111.56, right, and to make it kilonewton we can multiply as 10 to the minus 3, and this is becoming 227 kilonewton, which is greater than 220 kilonewton. So, this is okay, because the buckling strength of the wave is coming as 227 kilonewton, and the factor shear was given as 220 kilonewton. So, buckling strength is more than the factor shear. So, the section whatever we have chosen is okay. Otherwise, what we can do, if the section is not okay, then we have to increase the section size or we have to increase the bearing length. Either we have to increase the bearing length to accommodate this capacity, or we have to increase the section size, right. Now, we will check for crippling. So, crippling strength we can find out, say F w will be B plus N 1 into T w to F y w by gamma m 0. F y w is the yield strength of the wave. Now, F y and F y w is same here, because same material we are using, but if the material of the wave and flange are different, then we have to consider F y and F y w accordingly, and here F y w and F y is basically same. Now, to find out the crippling strength, we have to find out the value of B plus N 1. Now, B we know is given as 100 and N 1 we have to find out. N 1 will be, as we know, it will disperse with 2.5 slope, say for example, say crippling will happen here. So, we have to find out the dispersion, and this is T f and this is R 1, right. So, if we see because of the bearing at the support, so dispersion will happen like this. If this is the flange and up to this it is the root of the wave. So, it will disperse up to this with 2.5:1 ratio. So, we have to find out this is as N 1 and this is as B. So, B plus N 1 the length of this. So, I can find out N 1 as 2.5 into T f plus R 1, right, because with a slope of 2.5 it is dispersing. This is the assumptions we have made earlier. So, 2.5 into 11.4 is the thickness of flange and root radius is 16 mm. So, this is becoming 68.5 mm, right. So, now we can find out the value of F w. So, F w value will become 100 plus 68.5 into thickness of the wave is 7.4 into F y w is 250 by gamma m 0, and to make it into kilonewton we can multiply with 10 to the power minus 3. So, this is becoming 283.4 kilonewton, and this is also more than the shear force acting at the support, which is 220 kilonewton. So, we can say this is okay. So, this is how we can check for crippling, wave crippling and wave buckling, right. So, today what we have seen an example to find out a section size because of high shear. So, in case of high shear, what extra additional things we have done is the calculation of the reduction factor for bending moment, means bending strength calculation, right. So, only additional thing will be the reduction factor, and that reduction factor will be calculated based on the full bending strength, plastic bending strength and the plastic bending strength without shear area. So, from those data we can finally find out the modified bending strength of the whole section due to high shear. So, this is how we will calculate. So, thank you.